Prossimo presentatore è Pietro Battiston, un matematico diventato economista che usa pandas e mostrerà... Ah, questo è in inglese o in italiano?
Inglese.
Oh, sorry.
Cioè, come
the next speaker will be Pietro Battiston that will show us how to use pandas the wrong way for data processing and analysis.
Thank you very much. So yes, I'm sort of economist, sort of researcher, which actually means unemployed, but hopefully not for long. I actually propose to talk in Italian and English. I'm going to have it in English also because for the video it might be more useful. I don't like too much the title I put in English. In Italian it was Come usare pandas male, which more literally is how to use pandas in a bad way or badly. I don't like the title because it seems to suggest there is one wrong way to use pandas, while there are many, many wrong ways to use pandas. So don't take this talk as a particularly structured presentation of anything. I want to give some anecdotal evidence, let's say, but under the anecdotal evidence of usage, there is something which is interesting to understand if you don't know about the internals of pandas. Just give me 1 second. Okay, disclaimer. Pandas has bugs, quite a lot of them, and I was really impressed by this. And I really don't want to bash pandas. I love pandas, I use it all the time, so I say this only to say that you are very welcome to help fixing them. That said, it's a fact that pandas currently is very important, not just for my life, because I use it a lot, but also for other projects. And it's comparatively young. So it's really a project which is very powerful, but still has to settle some things. But this is not what I want to talk about in this talk, because it would be very easy to provide you with some examples of bugs, which maybe are solved tomorrow, and then this talk is useless, or certainly solved tomorrow. This talk is not even about necessarily wrong design decisions. Some of the things we will see are maybe questionable, but they are not necessarily wrong. And by that I mean there is some argument for having them like they are. What I really want to focus on is talking about a library which seems intuitive, but it's not always so intuitive just because it's doing complicated stuff, or anyway, more complicated stuff than one sometimes thinks. So just to make a comparison, NumPy is a very powerful and complex, in some sense, library, but it responds better to intuition, because more or less what you're doing is linear algebra. And there can be complicated linear algebra, but linear algebra is very well defined in some sense. You really know what to expect. Pandas has some things which make it which make the intuition generalize in non-trivial ways, let's say. Okay, and these were the slides of my talk. Because I prefer to show a bit of code. Okay, just for the records, I was not originally in the program. I was added a few days ago. I hope nothing's going wrong. Please accept my excuses if something is not perfect. Let's start with an example of what can go wrong on indexes. Okay, so let's import pandas. And let's create a data frame, which is basically a huge concatenation of a single data frame. You might say this is a quick way to prepare a data frame. Let's just prepare one block and repeat it. What's the problem with this? What is not nice in this database? Well, the name of the columns are not particularly nice, I agree, but still. The index is not exactly missing, but we are close to the problem. Let's look at 0. The index is not missing, but it's not unique either. And yesterday I was making this tutorial introduction to pandas, and they asked, what's the point of an index which is not unique? It should enforce the index to be unique. It should not allow you to do this ugly thing of having an index which is not really indexing in some sense because it's not unique. Well, that's a design decision that makes quite a bit of sense when you work with reshaping data, because you might have some index which at some moment is not unique, or you may just have some data which has a non-unique index. You still want to load it and do something with it. And usually the first thing you want to do is solve in some way the non-unicity of the index. But still, pandas allow you to make non-unique indexes. And in this case, it's just the consequence of me having repeated 2 times a block, including its index, which was from 0 to the size of the block. Now, what happens if I try to assign to a single label? So I would like to say I want a label with 11 and 7 fields, and it's not going to work. Why? Precisely because df lock 11 is not a single line, a single row. And since it's not a single row, even though I'm passing a single label, it's expecting a matrix 2 by 7. And this is just an example of the fact that if you have non-unique indexes, operations which seem quite trivial won't work. Well, for instance, this will work. Why? Because my index was from 0 to 100 to 99. So 101 is not there, so it's just going to add it. And that's another non-totally trivial thing of pandas. And I'll mention it now because I forgot to mention it in other places. But most of you probably know. So I had so let's recreate df. Df was this data frame which ended like this. Where was layout? Oh, no, okay. Okay, until 99. Now, if I do this, now it has one more line. Now, why is this not good? Well, it's good that in principle pandas allows me to do something that you cannot do, for instance, in NumPy. In NumPy, you're not gonna, let's show it. If I have an array npy zeros, shape, is it size or shape? I don't remember. 5,4, maybe shape. And then I say, so this is A. And then I say, you know what, add a line. So A4 is obvious. But now I say, okay, A6 is equal to 5, let's say the following one, is equal to 1, 2, 3, 4, no way. So arrays are immutable, or no, not immutable, obviously. I cannot change their shape. I can reshape them in several ways. Obviously, I can concatenate, slice, but I cannot just add a line. Pandas allows me to do this and to add a new line. It's usually something you don't want to do because it's very inefficient, because basically pandas is still based on NumPy and has a nice feature of being efficient because you have nice memory usage. But when you do this for a single line, you're asking to replace in memory all the metrics, and it's not good. So it's allowing you, but it's something you want to avoid. You would never want to add one line per time. Okay, this is also explained in the documentation. It's nothing very mysterious, but it's good to repeat. Okay, now let's look how so we saw what lock 11 gave. There were 2 lines. Okay. How much time do I use to get a line? 800 microseconds. Like I put this because pandas has several caching mechanisms. I don't want them to interfere. But if you want to be sure we're not having just luck, it's something between 500 microseconds and slightly over 1 second, depending on how lucky you are. Now let's take an identical. Oh, and by the way, we remember, right, that this returned 2 lines, okay? But this returns 1, because it's only the one I added. Okay. Let's try also the one which returns only a line. And it's 101. It's maybe a bit quicker, Yeah, it is a bit quicker. Okay, now let's look at the same index, except we reset the index. So since we reset the index, now the index goes until 200, so it is unique. Let's check. PDF.index that is unique. It is. Okay. And now let's make some experiments. So first, let's look in the original. I want this to be. Okay, now we already tried this, right? It was between half a millisecond and a millisecond. Let's try, but let me do it again so they are close to each other. Okay. Let's try with the other data frame. It's quite similar, but it's a bit slower, a bit faster. It's quite a bit faster. Okay. So retrieving, but you might say, okay, this is only a line. Let's try with 101. Okay. Here they are quite similar, okay? But already, if I happen to retrieve multiple rows, it's going to be slower. But let's try this. So now I'm asking a list with the same element, okay? This is around 1 to 3 milliseconds. This was quite faster on my version of pandas. It's still faster, but it's not as big the difference as expected. Anyway, that's just to say, on recent versions, this is basically going to be faster. But the thing is, when you have multiple indexes, it's not just something could be expected, but some things which work are less efficient. So in general, you don't want to have non-unique indexes. Okay. By the way, feel free to interrupt at any time if you have comments or questions. Okay, now indexes are the first obvious thing that pandas adds to NumPy. Now it was what most people happen to use pandas for in the first place, because it means having labels for stuff. But the other important thing that pandas adds to NumPy is the possibility to have in a single object, a data frame in particular, different data of different kinds. Okay, so let's try the following thing. We have two functions. Let's check this one, for instance. It makes a copy of the data frame. Now, you might not like the fact that I'm benchmarking with inside the copy, but trust me, it's not counting anything because it's very quick. And then for every index in my... Now, okay, let me make a step backwards. This is something obviously wrong because you never want to do in an explicit for loop something which could do vectorized. That's true in NumPy and that's true in pandas. So this is completely crazy because I could just say mydf a equal, for instance, mydf index times 2. But let's fake this is something interesting to do, okay? Because we have something here we are really not able to vectorize. This can happen. Or a function called by some other library which is not vectorized. Okay, then I make my copy, and then for every item in my index, I'm just setting a column to the value of the index times 2. Seems quite straightforward, right? Now, what do you expect? Okay, here is a different function, only in the fact that they added the list line. This line just says, first create the column, fill it with -1, and then do exactly the same thing. Okay? Will these two things return the same thing? No, if I ask, probably it's because they don't. Let me just restart. What's happening? So in both cases, I'm putting exactly the same data inside. Why is it that in this case I have a float and here I have an int? Well, it's pretty simple. It's that since the column A is not present, pandas is accepting my request to create it. So the first time this gets called, a new column is being created. Okay. Now this column is already filled in the first cell with an integer. Fine. What's the problem? What's in the other columns? Let's look. My df equal df.copy. My df. That's exactly the same thing. So this is basically the first call. A equal 0 times 2. Just to be really pedantic, it's exactly the same. Now the thing is, I told pandas to put 0 in the first cell, but I didn't tell it what to put in the others. So it's a missing value, which pandas represents as an n. But there are no missing values for integers. There are only missing values for floats, and this is not a decision of pandas, it's a specification of how numbers are represented in memory. So floats have a specific bit representation which indicates not a number. Ints don't. And so the only thing that pandas can do when you ask to fill a column, so for instance, if I had asked fill B with an integer, then no problem, it's always an integer and it's all filled. But if there are missing numbers, it's going to cast to float automatically, and then it's going to fill with integers. But even when it's all filled, it will remain a float, because it was a float in the first place and nobody asked pandas to convert back to integer. Now this is a problem not just because, yeah, they have different results, but let's look at the benchmark. They are not particularly different. Okay, they are comparable. But let's look at another example. So now I'm okay, no, sorry. What I should have said is they are not very different, but they are different, because here I'm actually running many iterations, so we can trust a bit the difference, and it is a difference. So this operation is taking some time, but not much. And the result is that I didn't cast to float stuff, which is an integer. Now let's try with this one. It's exactly the same, except that I'm setting the float value in the beginning, so it's going to be float afterwards. And it's more or less like the first. So basically, okay, what does it tell us? That basically what is taking time is not really this operation. It's rather the fact of casting. But let's try some more interesting example. So this is exactly the first. Excuse me, I'm a bit lost. These are the same. Sorry, no. So this notebook is over. So the lesson is just, if you work with integers, but this applies also to booleans, you don't want to have missing values. What's the right way to work with missing values? It's to have a value which you decide represents missing values, okay? So for instance, if I do my df, if I know that my data is never going to contain -1, I can safely use -1 to represent a missing value. And then I initially set the column to -1, and I just fill the values when I have them. Any questions on this? Okay. Now, okay. The types are not just a problem because integers don't have missing value. They're not a problem. They're a feature we must be aware of. But there can be also performance problems related to casting. So let's take this example. Here I'm initializing a data frame all of -1. Okay, it's a big data frame, but it's all integer. There's nothing particularly wrong in it. Let's check the types, all integers. Okay, now let's create a stupid function which returns a Boolean. And let's try to do two different things. In this case, we are asking if the element of the column, okay, we are going column by column. And we are asking, is this column even? And we are basically rounding to odd numbers, right? Yes, because if it's even, it's going to add a Boolean, which gets casted to integer, okay. This is even simpler. We are just including the information about whether it's even no. So there's one operation less, okay? Let's look at the performance. Okay, what's happening? There's one operation more and it's taking less time. Well, what's happening is that this is a Boolean, and while NumPy and pandas are perfectly aware that you can add a Boolean to an integer and get back an integer, well, when you ask pandas to just store a Boolean, it's just going to store a Boolean. It's not going to automatically cast. And this is another choice which makes sense, but can be unexpected. That is, you can sum Booleans, you can add Booleans to integers, but if you just want to store a Boolean in a previously integer column, pandas is not going to complain. It's going to just do it. And this is actually what's happening. The first column is, the first row is becoming filled with Booleans. And what's the result? Since in this column, for instance, we have a Boolean and an integer, the only object it could possibly take is the only dtype it could possibly take is object. And this is why it's very inefficient, because it's not just working with objects, it's actually casting changing the type of each column to object. So again, you want to be sure that you put coherent stuff inside, because pandas is not going to complain. It's quite happy to handle objects and to cast in smart ways for you. Is it a sign or no? Yeah, it's mine. Okay. But again, you must be aware of what's it doing, because it's not going to be efficient if you don't. And I mean, sometimes you don't care particularly about the efficiency. It often happens that you are happy to just load some data and have it loaded whatever it is, and then think about what's inside. But you must be aware that the possibility of handling multiple data types doesn't always come for free. Okay, and this is, I already showed an example with columns, but let's look at another one. So this is a data frame which is empty, has no columns, only 2 elements index. And I'm doing something vaguely similar to before, except that I'm filling the columns. Okay, there are no columns at all, and one at a time I fill a very stupid column, 2 integer numbers, I and minus I. Let's look how it looks. Okay, it's basically a column, the number minus the number. Let's check how much time it takes. My computer was a bit faster. Okay, 4 seconds. Now let's do the same thing, except we tell from the beginning that we're going to have 10,000 columns. Yeah, it's the same, right? So here I was creating one at a time. Here I'm saying, no, okay, just create them all at the beginning. And let's do the same operation. So this is an empty data frame. I'm setting the columns one at a time. So this in principle is smarter, because I immediately told him which columns to create. It's not. Why?
The first time you call it, I think, to create the columns.
No, the columns, let's check. The columns were already there. You have to. And it's true, they are none. But anyway, I should still fill with my integer. Well, they're not just nuns. They are nuns in object columns. Because I'm asking to create an empty data frame, and pandas has no idea whatsoever what I'm going to store in it. And you know what object accepts anything. Let's have objects. So I'm not exploiting fast number manipulation, basically. Okay, so let's do something saner. Let's create an empty data frame, not empty. Let's create a data frame in which we store initially -1, which is our code in this talk for missing value, integer missing value. And that's going to be a data frame of integers. Perfect. And this is significantly faster, okay? Because it's working with numbers, setting numbers, and all is fine. We can do the same with a float and then instead of an int. Okay. Why is it not working as efficiently as before? I'm actually setting integers in floats. Should be quite fine, no? I would expect it to cast to floats. Well, not exactly. Since I'm setting the entire column, and pandas has this concept that a data frame is not just a table. It's actually a series of columns. So even though here I'm giving just a normal list, pandas is understanding I'm creating a column. I'm replacing a column, actually. So this is not just setting elements. This is replacing a column. When I replace a column, and this new column has all the integer values, pandas says, well, you certainly want an integer column, and that's what is happening. And we can see it like this. So let's create a new one just to have everything clear. So this you usually don't have to look in it, but you better understand something of what it is. As I said, as everybody probably knows, pandas is based on NumPy, not just conceptually, but in the fact that under pandas you have a NumPy representation of data. This is stored in blocks. Why blocks? Because NumPy doesn't have a possibility of storing multiple types. So if you want a class data frame which is able to store multiple types, what you do is you create blocks of NumPy stuff. So they're going to be, for instance, this is a very simple data frame in this sense. It's big, but it's all a data frame of floats. And so if you look at the blocks inside of it, it's just a big block of floats. So it's also quite efficient in this sense. Now, what happens when I set a column to 0, 0, so it's going to take an integer value? It creates two different blocks. So as I told you, it's setting the column to integer because it thinks that's what I want. It's going to have a float block which has lost one column, and then an integer block which is new and which is just one column because it's a column I set. If I do the same with another column, I have two integer blocks. That already sounds suspicious. If this block is able to store 9,998 columns, why on earth this and this should be separate blocks and not the single block? Well, the reason is putting blocks together is not a trivial operation computationally. It takes some computational effort. So it's not done every time. So if I just add a new column, pandas won't reassemble in the memory in the best possible way for the representation of data in my blocks. It's just going to wait to see what I'm going to do with it. And again, if I create another one, I have one more block. And as you can imagine, if the strength of Panda in terms of efficiency is that it's based on NumPy arrays, when you have more NumPy arrays, then you're wasting something in some sense. Now, let's for instance ask, could be any operation, almost any operation, to take the maximum, okay? So it's taking the maximum over each column. Magic. All the blocks have disappeared. So basically, pandas is smart enough to understand that if I want to run an operation on a data frame, it's better have the blocks together, the block assembled in the best way. So basically what it's done is it took the 3 integer blocks, 1, 2, 3, and put them together in a single integer block, 3 times 2. So if I ask an operation, pandas first reassembles the blocks and then runs the operation. And so without even noticing, the blocks have been reassembled. But what happened in the original function was that I was not running any operation. It was just creating one column at a time. And every time it would take away a column from the big block of floats and create a new block of integers. And this takes time. And this is what made this operation so slow. Okay, I think I'll proceed to the next because there's not much time. This is just really an anecdote if you want. I create a data frame which is not particularly nice, but not particularly awful either. It's in the sense that there are different data types, fine, but that's what pandas is for, right? So let's have a data frame with different data types. And to be precise, we have an integer, a float, then a string which is represented as an object in pandas, which is stored as an object, and another integer. Now, dfmin does exactly what I expect, actually, maybe more than I expect. It's taking the mean of numbers and it's dropping strings. Perfect. So smart. dfmin, like many other functions, accept an axis equal 1, an axis argument, which basically tells it whether I want to take the mean over columns over rows, right? And again, it's very smart. It's just dropping the string column and it's taking the average of all the rest. Nice. So this is true, I guess. No? Right. So taking the average over columns is the same as, or wait, is it the reverse? Taking the average over columns is the same as transposing and taking the average over rows. No. What's the problem? The F transpose is a matrix which on columns has an integer, a float, a string, an integer. What D type could it possibly have? Object. There's no other way. D types. Okay. So what's happening is that Panda is saying, you're asking me to take the mean of object stuff. They are not numbers. I won't take any mean. I will just drop everything. And this is, again, might be unexpected, but it's you don't want pandas to check if every object is actually a number. It would be crazy. You just want it to drop objects. And this means that since you can have different types on columns, a transpose is not always as trivial as it seems. This is the same. Okay, this is a very quick spot. So everybody, or maybe many people, know that pandas is very good at group by, and in particular apply is a very useful function. Now, that might be my subjective experience, but for years I used apply because it's so powerful that you just put in any function you want, and it's doing the right thing. Great. Now, the right thing might be different things, because sometimes you want to apply a function which takes a group and, for instance, extracts the statistics, like NP mean. Other times you want to take a function which takes a group and extracts, for instance, let's say the difference from the mean of the group. So it's not creating a statistics, it's creating a group with the same shape but different data. Now, the thing is, apply does everything of this and much more. Sorry. And it does it relatively quick. Okay, 88 milliseconds. Just for the records. Okay, no, I'll tell you later. But there's a much better way to do it. So applies is very powerful, and group by as an object is a very powerful thing because it's really a lightweight way of grouping data in the computational terms. But apply has to really guess a lot of stuff. What I'm going to return, how do I want to assemble the result together. Aggregate is instead made precisely for the purpose of taking something from a group, and this something is typical statistic, for instance. And so it's much more efficient. Apply does both what aggregate does and what transform does. But aggregate and transform, if you know what you're doing, are quicker. Okay, I'm almost done. Let's just look at this simple example. Now, I call it don't be fanatic because, panda structures are great, but they are not meant to be abused. So here I'm just creating a simple data frame with many rows A space B space C. And then I want to split them. There are better ways to split them, but bear with me for a moment because it's what I want to show. So I could either apply to each row a function that takes the row and splits it and then takes a series out of it. You know, it's cool. I'm just creating a data frame out of series. It makes a lot of sense, right? Or I can just skip the series, and it's much faster. So a series is a very nice and powerful construct, which has a lot of overhead, which is worth, in some cases, not in others. So when is it worth? Well, basically, a series is wasted if you have no index or you have a trivial index. And this is exactly the case, because the index is going to be 0, 1, 2. In these cases, there's no reason to instantiate pandas objects, in particular if you are doing it many times. Okay, and this is the last. So maybe you know, if you use pandas, you probably know HDF. It's a wonderful format, it's very quick, it allows you to compress data, it's still pretty quick with compressed data. So I use it a lot when I have big data sets, because it's not just faster than CSV, and it has more possibilities of compression. It's also nicer because it really keeps the structure of your data. In this trivial thing, in CSV, if you have an index, you have to tell when you reload pandas that it's an index. HDF is wonderful, automatic. You just store the data and get it back quite efficiently. Quite efficiently, in the sense that, again, this has an overhead. So let's create a directory and let's take 1000 stupid series from 1 to n and store them in CSV in a directory. And let's do the same thing with AGF. So instead that in a directory, it's going to be in a single file. So it's also nice, no? Single file instead than 1000 files scattered in the file system. Well, sort of. The HDF file is taking 12 megabytes, the directory is taking 5.8. So HDF is really a wonderful format, but it has some overhead. So in some cases you don't want to use this, in other cases you want to use it maybe in some smarter way. For instance, you could try to aggregate all the series in a single series and save that, or there are many possible ways. It's not optimal to have a lot of small objects because each of these has an overhead in terms of stuff on data, and it's not even particularly efficient to do this computationally in the sense of time needed to execute. And that's it. I'm sure I forgot many other interesting cases of unexpected things in pandas because I find some every day, but these are the ones I wanted to cover. Thank you.
So we don't have much time for Q&A, but I think we can take a couple of questions. Okay.
A very stupid one, sorry.
I don't believe you.
When you use timeit, this is substituting for... So you mentioned yesterday that either you get printed the result or you are modifying an object. Yeah. In this case, timeit is cancelling for the printed output,
Yeah.
but you're not modifying.
Well,
right?
time it, just execute code, and if there is some output, drops it.
Okay.
So it does. I can have operation which modify the object. I can have so in place operations basically, or I can have operation which returns something. And for time it's not important.
Other questions? We have some time.
If you want any curiosity of pandas internals, for what I know, obviously. Okay.
Okay, so thank you again.
Anyway, if you have any curiosity, I'm here today and tomorrow. Thank you.